Welcome to the second of my RISC-V tutorials. This session covers emulation and simulation. These features are necessary during the development stage when actual RISC-V hardware is not available or even desirable. One caveat is that not all architectural extensions may be implemented. For example, v32i simulation will not work when trying to use 64-bit or floating point instructions. This, however, is also the case with hardware. Again, check the manufacturer's spec sheets to verify which features are supported. 3 hardware platforms that appear to work well include 1. The Vision2 RISC-V single-board computer, Starfive JH7110 processor with integrated 3D GPU and 8GB memory. 2. The Lychee Pi 4 with 64-bit LPDDR4 memory, single-board computer. 3. The Banana Pi BF3 single-board computer. These systems have support for Linux and the necessary QEMU tools that used in this set of tutorials. The companion book shown at the end of the video to this series discusses candidate hardware in more detail as well as the product URLs. The first emulator that will be discussed is the Quick Emulator QEMU. The following steps can be performed to configure a Fedora-based virtual machine. The emulation will be configured on an x86-64 Linux system running Fedora Workstation 42. Different software revisions may have to be tweaked accordingly. These installation steps are documented at the Fedora project wiki. If a Linux system is not available, then a virtual machine can be created using a Windows-based emulator. This is termed nested virtualization, where a virtual machine hosts another guest virtual machine. Note a reasonable degree of Linux experience is expected to perform the installation tasks presented here. To install QEMU, type the following commands and select Enter. This will install the necessary files to get the emulator set up. Installation time is usually around 2 minutes, but is dependent on your infrastructure. In case of any issues, consult the most up-to-date steps from the Fedora wiki. After installation, set the current user's group membership as shown and write information to the configuration file. Finally, reboot the system. Once the system is rebooted, the virtual machine can be created. The wget utility will fetch the Fedora image and load it into the current directory. If wget is not available, it can be installed with the dnf command. Next, move the downloaded image to the default images directory. The virtual machine will be created using a YAML file, which specifies some basic settings. Make a change into the RISC-V directory and populate the user-data.yaml file with the settings shown. After the YAML file has been edited, start the virtual machine with the script instruction parameters displayed. Note that some of these parameters can be altered. The script uses 8 GB of RAM and 4 virtual CPUs. These can be increased or decreased accordingly. The creation time is fairly short, approximately 2 minutes. Once the VM has booted, log in with the username Fedora and the password Linux. Perform some preliminary checks to see the memory and storage capacity using various commands such as lsblk and free to show disk configuration and memory availability. Run the ls-cpu command to show the machine architecture. If all goes well, a 64-bit RISC-V virtual machine will have been created. More architectural information is shown with the cat/proc/cpu info command. Here it shows that there are 4 virtual processors, and they support a number of extensions, including single and double precision floating point. Next, we'll attempt to code a small RISC-V assembly program and execute it. At this point, do not be concerned with the actual code, as this will be covered in the next tutorial. The end goal here is to verify that the emulated RISC-V system will be adequate for our needs. Create an assembly language source file with the commands shown. Assemble the file using the AS command, and we can see that the command failed. This is because the Fedora cloud image that was downloaded is fairly minimal and does not include the necessary files. Fortunately though, our system has network access, and we can simply download the tools. Enter the command sudo dnf bin utils. This will install the missing utilities. Retry the command, and it executes silently. Running ls shows that a new file with the .o suffix has been created. This is the object file containing the assembled binary code. The next task is to link the file so that it can be loaded into memory and executed under the Linux operating system. The change mode command ensures that all users have the permissions to run the file. The output shows the text "Hello RISC-V." The virtual machine can be shut down with the command sudo power off or rebooted with the command sudo reboot. To start the system, use the command versh start fedora RISC-V -console. If -console is omitted, then the system will be accessible remotely rather than interactively displayed. Although the system can be used as is, it is recommended to update the system software and increase the virtual storage space. The virtual machine when generated is quite small in terms of storage capacity. It is possible to enlarge this image if the umbrella host system has enough storage. To do this, ensure that the VM has been powered off and issue the command QEMU-image resize/var/lib/images/fedora-risc-v.cow2+20g. Restart the Fedora VM and run the fdisk program on the VDA virtual disk. Extend the system with the resize command, using partition 3 and accepting the default capacity as shown. Show the new capacity with the printp command and use W to write out the changes. Reboot the system. CPU Later is an excellent online simulator, perfect for learning as it shows aspects of the system state during program execution. It allows single-step execution so users can track changes in registers and memory as the program runs. The simulator supports several architectures including RISC-V with features like multiplication, division, and floating point operations. It has 3 main tab windows for editing source code, disassembly, and memory. On the left side of the screen, there's a panel displaying registers, which is helpful to observe as the program executes. The source window provides a template with the first 2 lines of code, and there are program run buttons at the top, such as step into, continue, and restart, which enables easy program control. To get started, enter the code in the editor, then select compile and load at the top. A message below the editor confirms successful compilation, and the main window will display the disassembled source code instructions. Select the Step Into button to run the program. The code initializes register T1 with 0 and T2 with 10. It increments T1, compares it with T2, and if they are not equal, it jumps back to the ink label to increment T1 again. This loop continues until the registers hold equal values, allowing the program to exit the loop. RISC stands for RISC-V Assembler and Runtime Simulator. It requires Java to be installed on the target machine and can be downloaded from the URL shown. Start RISC by issuing the command java-jar RISC1_6.jar. First thing we're going to do is edit an assembly language program. Edit the code shown. And select Assemble. And it should complete successfully. After this, adjust the run speed. This can be done at full speed or in small increments. Set this value to your own preference. Hit go, and then watch register T1. This will slowly increment until the register T1 equals the value of T2. At this point then, the program will exit the loop and terminate. The program memory can be examined, or you can look at the text data section. This is just where the program is loaded, and you'll actually see the hex values corresponding to the instructions in this location. There are a number of settings available. For example, the architecture can be set to 32-bit if you want. So if we run the program again, then you'll see that everything is happening on 32-bit wide registers as opposed to 64-bit registers. Select Run, Go, and you can see here again, register T1 is incrementing. This will increment up until it reaches the value 10 or hexadecimal A, and then it will exit the loop. The next topic is cross-compiling. Previously in this tutorial, the systems emulated or simulated the RISC-V architecture and provided a RISC-V development framework. Cross-compiling involves writing the code on a different architectural machine than the one that it will ultimately run on. An example is developing code on an x86_64 host to generate a non-x86_64 executable. Although the executable will not run on the x86_64 host, it can be transferred to a native RISC-V system for execution. There is an official RISC-V simulator called Spike, which can be used to run these cross-compiled programs. Typically, programmers will use Spike for initial development and then test their final releases on a native host. The steps following detail how to develop code on an Ubuntu x86-64 system, which will run under a RISC-V environment. The first step is to obtain the RISC-V toolchain. The toolchain includes the necessary tools to develop RISC-V code. Since the host will now house multiple development sets of tools, it will be necessary to specify which assembler, linker, etc., is to be used. The commands for assembling and linking are similar to the commands that run on a native host. To differentiate the RISC-V tools from the, in this case, x86-64 tools, they are preceded here with RISC-V 64-unknown-elf- tool. Basically, Spike is a RISC-V instruction set simulator that can execute RISC-V binary programs on non-RISC-V systems. It lets the programs run as if they were executing on RISC-V native hardware. Proxy kernel PK provides a lightweight kernel that can handle system calls from RISC-V binaries. Spike and PK work together to provide a working framework for the code on non-native RISC-V hardware. The RISC-V toolchain provides counterparts to native compilers, assemblers, linkers, etc. To generate a RISC-V C program, the command RISC-V 64-unknown-elf-gcc file name would be used. To link RISC-V object files, the command is RISC-V 64-unknown-elf-ld file name is used. There are other components that can be used in bare metal environments where no operating system is present. This is important for embedded system developers. In our case, we will focus on using RISC-V under the domain of a Linux system. Prior to installing the toolchain, Spike, and the proxy kernel, a number of housekeeping tasks are necessary. These tasks involve downloading and installing libraries and utilities, configuring user permissions, creating directories, and modifying the path variables so that our system knows where to find the programs. Follow the steps in the screen showing. After this, the toolchain Spike and PK can be downloaded from GitHub. The GitHub URLs are shown towards the end of this video. The longest part of the process is building the toolchain. This is system dependent and can take correspondingly longer if virtualized machines are used. Building Spike and the proxy kernel is relatively faster. The steps described can be copied and pasted from the README text, which can be obtained from the URLs at the end of the video. The next few screens show extracts of the installation process. Expect the process to take anywhere from 1 to 3 hours depending on your hardware. The first part downloads and installs the support files. Next, the toolchain, Spike and PK are cloned from GitHub. After the files have been cloned, the toolchain is built using the make command. As mentioned earlier, this is a lengthy task. The toolchain should be installed and working correctly at this point. It can be tested by issuing the command RISC-V 64-unknown-elf-gcc-v. This should return the version number, which in this case is 15.1. Write a simple C program called Hello RISC-V as shown and compile it with the command RISC-V 64-unknown-elf-gcc hello RISC-V.c. Since an output file name was not specified, the default name is a.out. Investigating the format of a.out shows that it is as expected in RISC-V format. If we try and execute it on the x86_64 host, it will naturally throw up an error. To verify that the program works, it needs to be copied over to a system with the correct 64-bit RISC-V architecture. In the screen above, the file is copied over to a Banana Pi BF3 host. Once the copy is complete, the file can be executed on the Banana Pi. Running the lscpu command shows that the architecture is indeed RISC-V 64-bit. Executing a.out now prints out the string hello RISC-V. Now that the toolchain has been installed, it is time to build and install Spike. Once Spike has been installed, it can be tested by issuing the Spike help command. The last step is to build and install the proxy kernel. If there are any issues running the programs, check that the paths and permissions have been set up correctly. Ensure that the software has been installed in the expected locations. The file a.out can now be run on the x86 host under the framework of Spike and PK without having to copy it over to a RISC-V system. This use of Spike greatly shortens development time. To summarize, this tutorial has laid out a number of options for subsequent tutorials. If you can procure a hardware-based system, this is probably the best route to take. If not, a number of emulators and simulators have been covered. To get the most out of these videos, treat them as follow-along tutorials, rather than passively watching. The listed resources are helpful references when working through this tutorial. We have now reached the end of Part 2. Part 3 starts to introduce RISC-V programming. There is a focus on memory interaction, and GDB is covered in some detail. Hopefully, this will point you in the right direction to get set up for the upcoming sessions. There are many options available to learn programming on RISC-V. My preference is to use native 64-bit low-cost single-board computers, but you can use emulators, simulators, Spike, or even precompiled cross-compilation binaries, which avoids the lengthy build process that we have seen here. In the next tutorial, real executable RISC-V programs will be edited in a real programming environment. The assemble, link, and debug cycle is shown along with memory to register interaction. Again, many thanks for watching. Links to these tutorials and companion PDF books can be found at the website risccomputing.com. See you in tutorial 3.